This video is about the ideal gas law. Now, when you are looking at a gas problem, one of the things you have to do is figure out which equation to use. So when we look at this one, if you have 0.56 moles of an ideal gas at 87 degrees Celsius and a pressure of 569 torr, what volume will the gas take up? All right, so we have a couple variables in there. Now, there's a couple different laws that we have been given in this chapter. One of them is P1V1 over T1 equals P2V2 over T2. That's good for the combined gas law. We can also adjust that to get Boyle's law or Charles' law. We have the ideal gas law, PV equals nRT. We have Dalton's law, which talks about the partial pressures of gases adding up to be the total pressure. And then you have Avogadro's law, that's 1 mole of a gas has a volume of 22.4 liters at STP, regardless of what gas it is. So when we look at this problem, well, we're given moles, so that has the abbreviation of N. We have a temperature, we have a pressure, and it's asking for volume. Notice it doesn't say anything about any of those variables being changed. There's no second pressure or temperature or volume. Nothing's talking about conditions at STP. So that means the combined gas law along with Boyle's and Charles are out. There's nothing about partial pressure, so that excludes Dalton's law, and it's not at STP, so we can't use Avogadro's law for this either. So that means we are using the ideal gas law. The one thing that's not mentioned in the problem is this R, and R for us is the universal gas constant. It is 0.0821 liters atmospheres per mole K. So since R has those specific units for us, we have to make sure the units in the problem match the units for R. So moles is good. The temperature is given in Celsius, so we have to convert that to Kelvin. The pressure's in torr, we have to convert that to atmospheres, and we're going to solve for volume. All right, so first thing we want to do is some conversions. The temperature is easy, 87 degrees Celsius. You want to convert that to Kelvin, so you add 273. Since 87 is a whole number, we round our answer off to a whole number. You get 360 Kelvin. Now for the pressure, 569 torr. We want to convert to atmospheres because the units for R have atmospheres in them. So since you start off with torr, you put torr on the bottom, you put atmosphere up top. We use the standard pressures. It's 1 atmosphere is the same as 760 torr. You do the math for this, round it off to 3 significant digits because that's what the number has. 569 has 3 significant digits. You get 0.749 atmospheres. All right, now we're ready to use the ideal gas law equation. You have PV equals nRT. We are solving for volume. So you could just rewrite this for volume. If you want volume by itself, what you have to do is divide both sides by pressure. So you get nRT divided by pressure. And we can plug in the numbers we have right now. 0.56 moles. R is the universal gas constant, 0.0821 liters atmospheres per mole K, and we have the temperature in Kelvin is 360 Kelvin. All that is over the pressure, which is 0.749 atmospheres. Now if you pay attention to the units, moles cancel out, Kelvin cancels out, atmospheres will cancel out, and the only thing that doesn't cancel out is liters, which is what we're looking for. When you round this off to the least number of significant digits, 0.56 has 2 significant digits, so our answer becomes 22 liters. And that's what the volume would be. All right, a lot of times people have a hard time starting off, but think about what equations you have to work with, and then look at what variables you're given in the problem. Let's move on to the next one. All right, 4.25 moles of a gas at a pressure of 5.65 atmospheres and a volume of 12.0 liters. What is the temperature? Again, there's no mention of a second pressure, a second volume, or different temperatures. So we can't use P1 V1 over T1 equals P2 V2 over T2. There's no partial pressure. It's not at STP, so that knocks out Dalton's and Avogadro's law. So we are going to end up using the ideal gas law. And the other way you could tell that you wouldn't use Charles or Boyle's or the combined gas law is they don't really have anything to do with moles either. Now, we need the units in the units for R, which is liters atmospheres per mole K. We have liters, we have atmospheres, we have moles. So this should work out. We don't have to do any conversions. This problem is going to be pretty straightforward. We want to solve for temperature. So if you want to get temperature by itself, you have to divide both sides by NR. So you get PV divided by moles times R. All right, we could plug in the numbers since the units match. 5.65 atmospheres times the volume, which is 12.0 liters. It is 4.25 moles. And the universal gas constant, 0.0821 liters atmospheres per mole K. All right, I like to double check the units to make sure everything's in here right. Moles will cancel out, atmospheres will cancel out, liters will cancel out. The only thing not canceling out is Kelvin, and that is what we're going to end up getting. So when you do the math for this, make sure you do it in the right order. Use parentheses if you have to in the calculator. What you should end up getting rounded off to the least number of significant digits that are given in the problem, which they're all 3. So you get 194 Kelvin. Since the problem doesn't ask for the answer in Celsius, I'm just going to make it easy and keep it in Kelvin. I like to put the units for R in the problem because I always like to double check that my problem is set up the right way to make sure things cancel out how they're supposed to. I know it gets a little annoying if you're doing a lot of problems to keep putting the units in, but it is a good way to double check that you have it set up right. All right, last one. A sample of argon gas at STP occupies 56.2 liters. Determine the number of moles of argon and the mass of the sample. All right, now STP is telling us a couple things, standard temperature and pressure. So that's 273 Kelvin and 1 atmosphere. So now we have pressure, temperature, volume, and it's asking for moles. All right, and it wants us to know the mass of the sample. Okay, so what we could do, we have PV equals nRT. N equals PV over RT. We want to solve it for moles, so we rearrange it, divide both sides by RT, and what you get is 1 atmosphere times 56.2 liters liters atmospheres per mole K, and that gets multiplied by the temperature since it's standard temperature. That's 273 Kelvin. All right, when you do the math for this, Kelvin cancels out, liters cancel out, atmospheres cancel out. What you're left with is moles. You get 2.51 moles rounded off to the least number of significant digits. And the only significant digits given is this liters. That's 3 significant digits. All right, so that gives us 2.51 moles of argon. Now, what the problem is asking us for, though, is moles and mass. So what we could do is take that 2.51 moles of argon, multiply it by the molar mass. Since you start off with moles, moles goes on the bottom, mass goes up top. You get 1 mole is 39.9 grams. You get that number off the periodic table. And you get 100 grams of argon as the answer. Now this problem says at STP. Now since it says at STP, there's actually another way you could do this problem. Not all ideal gas laws can be solved two different ways. The only reason why you can do this problem a different way is because it says at STP. If it is not at STP, the way I'm going to show you now won't work. Alright, so at STP is a key part here. We know that at STP, 22.4 liters, well, I should say 1 mole of a gas takes up 22.4 liters. Again, that's only at STP. So if we wanted to, we could use Avogadro's law to solve this problem. 56.2 liters of argon. So just start off with liters, to put liters on the bottom. All right, we have liters of argon per mole of argon. And we have the conversion factor right up here, 22.4 liters. Now, since it's asking to determine the number of moles of argon and mass in the sample, we can do this as two different steps. 56.2 divided by 22.4 gives us that 2.51. Now, if the problem was only asking us for mass of the sample, what we could do is actually just combine the two steps and basically turn it into a stoichiometry type of problem. So now what you would have is 1 mole of argon is 39.9 grams of argon. And then basically you have the same answer as what we had that I previously erased, 100 grams of argon. It's a little quicker doing it this way, but like I said, you have to be careful. This is specifically at STP. If it was not at STP, this conversion factor would not work. It has to be at STP for that one to work. So pay attention to the wording. I showed you two ways to do that one, although not all ideal gas laws can be done two different ways.